Hello everyone, this is Professor Roman. Let's continue the group theory lectures. We're ready now for chapter 11, symmetric groups. I suppose this chapter should be called more on symmetric groups because we've already discussed these groups in some detail, but I did leave out some proofs and there is more to say about them, considerably more. After all, they are the most complex family of groups because they contain copies of all groups. So there's quite a lot to say about the symmetric groups. Just as a reminder, in chapter 3 we did discuss the following. Disjoint permutations commute. That was theorem 3.1. The order of a permutation in Sn is the least common multiple of the cycle lengths in the cycle decomposition of the permutation. That was theorem 3.4. Two permutations are conjugate in Sn if and only if they have the same cycle structure. And that was theorem 3.13. We did state in chapter 3, without proof, but with an example, that every permutation has a cycle decomposition and that the decomposition is unique up to the order of the factors. So let's prove that now. So let sigma be in Sn and define an equivalence relation on the underlying set for Sn, which is 1 through n, by x is equivalent to y if y is equal to sigma to the kx for some integer k. I'll leave it to you to show this as an equivalence relation. For little x in the index set, or the underlying set I, the equivalence class containing x is generally called the orbit of x. And it looks like this. It's really just the set of all sigma to the kx as k ranges over z. That is, after all, the definition of equivalence of two elements, x and y. So this is the set of all elements that are equivalent to x. Since I is a finite set, if we start with x and we continue to apply sigma, eventually we will encounter duplicates. So we'll have sigma to the ix equals sigma to the jx for some I less than j. And so sigma to the j minus I fixes x. It sends x to itself. Okay, that's good. What to do? Well, the extreme witness principle would suggest that we take a look at the smallest positive integer, m, for which sigma to the m x equals x. And it's not terribly difficult then to show that the orbit of x is this set, x sigma squared x up to sigma to the m minus 1x. Sigma to the mx is equal to x. So we get nothing more if we continue to apply positive powers of sigma. And I'll leave it to you to verify that negative powers of sigma applied to x also does not yield anything other than this set. The restriction of sigma to the orbit of x is then this m cycle. And the distinct orbits, since they are equivalence classes, form a partition of I. And so sigma is nothing more or less than the product of the disjoint cycles of this form as the orbit of x varies over all the possible orbits. If you vary over x, there are m elements that give you the same cycle, so there's a lot of duplicates. We just want the distinct orbits. And then the cycles that correspond to those orbits, their product will be sigma. So that is the existence portion of the theorem. The cycles are disjoint, and you get the product of disjoint cycles. As far as uniqueness is concerned, if you have a cycle decomposition sigma, say alpha 1 through alpha m, and if x is in the underlying set I, then there's got to be an integer k here, in fact a unique integer, for which x belongs to the support of alpha k. These supports are disjoint, and their union is all of I. So one of the cycles here has x in its support. So actually it's in the underlying set. In case alpha k is one cycle, then it's not moving x. And so this should really be the underlying set. There is a difference between the underlying set and the support. Okay. So alpha k then has x in its underlying set. And as we apply powers of alpha k, we will get the entire cycle alpha k. The cycle contains x, and therefore it contains sigma x, which is the same as alpha kx. We could look at it this way: restrict alpha k, that cycle, to its underlying set. Then this is the description of what alpha k does to x as you apply it. It sends x obviously to alpha kx, and alpha kx to alpha k squared x, and so on. And then this will wrap around. And because the application of alpha k is the same as the application of sigma, as long as the element you're applying it to belongs to the underlying set for alpha k, otherwise that wouldn't be defined, this is equal to this, which is in fact the orbit, sigma restricted to the orbit of x. So each of these cycles is uniquely determined by sigma. It is sigma restricted to a particular orbit of x. So all cycle decompositions have the same cycles in the product. They may be in different orders, but they're the same cycles. And that's the uniqueness part of the theorem. I wanted to also mention another result. You know, the symmetric groups are quite amazing, and that shouldn't be a surprise since they contain isomorphic copies of every group. So there's a lot going on in the symmetric groups. And they even have some interesting surprises, and I think you might find this one kind of interesting. We do know, of course, that any permutation can be written as a product of transpositions, and in general those transpositions will not be disjoint, or pairwise disjoint. But for n bigger than or equal to 4, every permutation sigma in Sn is actually a product of two permutations of order 2. And another way to say that is that sigma can be written in the form sigma equals alpha beta, where both alpha and beta are products of disjoint transpositions. So while we can't write sigma as a product of disjoint transpositions, we can write sigma as a product of two permutations, each of which is a product of disjoint transpositions. That's the closest we're going to get to a product of disjoint transpositions. We've also seen that if n is at least 2, then every cycle in Sn, and therefore every permutation in Sn because of the cycle decomposition, is a product of transpositions. And we verified that because of these two formulas. This cycle can be written as a product of transpositions. This one cycle can also be written as a product of transpositions. And we discussed the fact that this representation is far from unique, but that the parity of the number of transpositions in any transposition decomposition of sigma is unique. This is a very famous theorem, and there are many different proofs. Here is one of them. Call this the Parity Theorem. If sigma is in Sn, then exactly one of the following holds. Sigma can be written as a product of an even number of transpositions, in which case we say sigma is an even permutation or has even parity. Sigma can be written as a product of an odd number of transpositions, and then we call sigma an odd permutation. So here is the proof. Suppose that sigma could be written as a product of both an even number and an odd number of transpositions. So that would look something like this. Well, we can shove all the taus to the other side, and so the identity can then be written as a product of an odd number of transpositions. And we'd like to show that is false. That contradiction will prove the theorem. So to show that no such decomposition of the identity is possible, suppose it was. So the identity is the product of theta 1 through theta m. This is written out here. And m is odd and therefore at least 3. M certainly can't be 1. The identity is not a transposition. We can assume, just for convenience, that no two adjacent factors here are the same, because then they would cancel. Now the key observation in this particular proof is that if A1 here does not appear in any of the other transpositions, we have our contradiction, because then the right side here, this product, will send A1 to B1. The identity doesn't do that. It sends A1 to itself. So if A1 does appear elsewhere, not just in the leftmost transposition, we need to find some way to do something about that, so we can produce this very same contradiction. Well, the extreme witness principle prompts us to consider one of the extreme occurrences of A1. It's not going to be the first occurrence, so we'll look at the last occurrence, or the rightmost occurrence, which I'll mark with an arrow. So just to warm up, suppose that the rightmost A1 occurs in the second factor. So I put the arrow here under A1. What could we do now? Well, the product of these two transpositions, A1B1 and A1B2, is equal to A1B2 followed by, well, I shouldn't say followed by, it's the other way around, A1B2, B1B2. Remember, you apply B1, B2 first, so A1, B2 actually follows B1, B2. So I'll just say A1, B2, B1, A2, B1, B2. These are equal, and all I have to do is check and make sure they do the same thing to A, B1, and B2. So this can be rewritten here. Now, A1 is the only occurrence. This first occurrence of A1 is the only occurrence in the entire product, and we have our contradiction. So maybe some similar reasoning will work if the rightmost A1 appears later on in this product. So suppose it appears, say, in the kth transposition, where k is at least 3. So this is what the identity would look like, the decomposition. Here is the rightmost occurrence, A1, in the kth transposition. Well, remember that adjacent transpositions, we're assuming they're disjoint, because we would have, if not, we would have canceled them. And it leaves 3 possibilities for this adjacent pair that contains the rightmost appearance of A1. It's the kth transposition and the one just before it. If these 2 transpositions are disjoint, then the factors commute, and we can just move the second factor to the first position, and we have, you need to check that neither of these is equal to A1, could be equal to A1, and so we have in fact moved the rightmost occurrence of A1 to the left. If one of the components in this first transposition is equal to A1, we can assume it's, say, AK minus 1. These are just 2 arbitrary elements. Then we can do something similar. We can move the transposition. So we've got 2 A1s here. So what we can do is tweak this around so that A1 appears only in the left transposition. So you can check that these are the same. So again, we've moved A1 1 position to the left. The final possibility is that one of the components in this factor is equal to BK. BK is one of these. We've already ruled out the case where they're disjoint, which means there must be some overlap. So either A1 is one of these or BK is one of these. So that's the final possibility. And again, we can arrange it so that A1 is moved over 1 step to the left. Well, now all we have to do is repeat this process until the rightmost A1 is in the second transposition. That was the first case we considered, the warm-up case. That led to the contradiction. So this proof, it's not terribly deep. It's just a little bit of arithmetic or algebra with transpositions. The trick here, of course, is to see, make the key observation here. And once you've made that key observation, experience will lead you to say, well, maybe there's a way to arrange for this. That's how mathematicians think. It's kind of like the wish lists. They make wish lists. They make an observation and they say, gee, I wish this would apply in more generality. Okay. So the proof is, a little tedious maybe, but not mathematically deep. the fact that any permutation in Sn is a product of transpositions can be restated by saying that Sn is generated by the family of transpositions. And as I mentioned in chapter 3, I guess, there are a variety of other generating sets for the symmetric group, and they can be very handy under the right circumstances. And here is a sample. There are 5 different generating sets for Sn. The first is a set of transpositions. We know about that. Also, the set of transpositions of 1 will generate all permutations in Sn. So this is what they look like: 1, 2, 1, 3, up to 1n. So that's a remarkably small set, but it's going to get even smaller. The adjacent transpositions generate Sn: 1, 2, 2, 3, 3, 4, and so on. Here's a generating set with only 2 elements: the full cycle 1 through n and the transposition 1, 2. Another one, the cycle 2 through n and any single transposition of the form 1k, where k obviously has to range between 2 and n. As to the proof, one way to show that a set, call it X, of permutations generates Sn is to show that X generates the members of a known generating set. So, for part 2, for example, the transpositions of 1, we just have to observe that any transposition AB has this, can be written in this form: 1A, 1B, 1A. And just for practice, let's verify that. This side sends 1 first to A. This doesn't touch it, then A goes back to 1. So 1 is fixed, as it is on this side. A goes to 1, which then goes to B, to left alone. So A goes to B, as it does on this side. And finally, B goes to this, unmoved by this, moved to 1. 1 is moved back to A. So B goes to A, just like this side. So the transpositions of 1 generate all transpositions, and therefore they will generate all permutations. For part 3, the adjacent transpositions, if we use capital A, and I'm kind of sorry I did because I don't mean the alternating group. If capital A is the subgroup of Sn generated by the adjacent transpositions, then 1, 2 is in A, and if 1, because that's an adjacent transposition, if 1k is in A, for some k bigger than or equal to 2, then so is 1k plus 1, because you can write it this way: kk plus 1, 1k, kk plus 1. This we're assuming is in A. These are adjacent transpositions, and so are in A. And so 1k plus 1 belongs to A. So this is a little mini induction, if you want. 1, 2 is in A, and if 1k is in A, so is 1k plus 1. Therefore, every transposition of 1 belongs to A, and so A has to be Sn. So the adjacent transpositions generate all the transpositions of 1, and therefore all permutations. For part 4, again, let A be the subgroup of Sn generated by these 2 cycles, the full cycle and the transposition 1, 2. Then the adjacent transposition 1, 2 is obviously in A, And if this adjacent transposition k minus 1k is in A, so is its conjugate by a cycle that's in A. So, but this conjugate, if you take this conjugate, to conjugate a cycle by a permutation, you apply the permutation to each member of the cycle. So it just kicks k minus 1 up to k and k up to k plus 1. So A then contains all of the adjacent transpositions, and therefore by the previous part generates all of Sn. Part 5, I'm going to leave for you to contemplate. I'm not going to go through the proof. It would be good practice for you to do that. I probably should have left it as an exercise, but the alternating group also has a very interesting and very important generating set. An, for n bigger than or equal to 3, An is generated by the 3 cycles. As to proof, any even permutation is a product of pairs of distinct transpositions. It's a product of transpositions because of the transposition decomposition that applies to any permutation. But since the permutation's even, there has to be an even number of transpositions. And we could cancel adjacent transpositions that are the same, so assume we've done that. Then we can just simply group them in pairs without reordering. Okay? So that's where this statement comes from. If two transpositions that are adjacent have an overlap, they would be of the form ABAC, but that is a 3 cycle. If two adjacent transpositions are disjoint, then we can arrange for overlaps. ABCD is AB, BC, BC, CD. These cancel because they're in. This is an involution, and that is the product of 2 3 cycles. So we can arrange for each pair of transpositions to be written as a product of 3 cycles. So the whole thing is a product of 3 cycles. I also want to discuss a little more the relationship between AN and SN and gigantic subgroups. AN sits very comfortably inside SN. It's a gigantic subgroup of SN, has index 2. And what we're going to show is that AN is in fact the only gigantic subgroup of SN. Moreover, a theorem from chapter 8, 8.30, implies that any subgroup of Sn is either completely contained in An or else it is half in and half out of An. Or in other words, every subgroup of Sn either contains only even permutations or exactly half of the permutations in the subgroup are even. It's 50-50, even and odd. An itself doesn't have any gigantic subgroups. So let's prove all that, and it doesn't take very much. Why is An the only gigantic subgroup of Sn? Well, if H is a gigantic subgroup of Sn, then that theorem from chapter 8, another thing it said was that the square of any permutation must be in H. So the squares of all the 3 cycles are in H. But any 3 cycle, ABC, is the square of another 3 cycle, ACB. So H contains all the 3 cycles, but the 3 cycles generate AN, so H has to contain AN. It's a proper subgroup of Sn. It contains AN. It has the same size as AN, half the size of Sn, so H is actually equal to AN. As far as part 2 is concerned, if A had a gigantic subgroup, I'll call it H again, then since the 3 cycles are even permutations, the same argument here tells us that all 3 cycles lie in H. Therefore, H is AN, which is a contradiction to it being gigantic, because it would have to be half the size of AN. So AN has no gigantic subgroups.